about the reversible steady work. The work done during a process depends on the path followed by the gas or the material or the system, as well as on the properties of the system at the end states. So, for example, this expansion of this gas will depend on the process path as well as the end states. If the process path involves lots of friction between this piston and the cylinder, then the work done will be affected by this. And we know that from previous chapters. For a reversible quasi-equilibrium moving boundary work associated with a reversible system, this will be the case. The boundary work is just difference in pressure. This quasi-equilibrium work interaction leads to maximum work output for work-producing devices and minimum work input for work-consuming devices. So maximum for example, turbines, and minimum for pumps and compressors. Why do we say that? Because if the expansion involves no friction, no work lost due to friction, to overcome friction and to overcome or deal with unrestrained expansions and all types of irreversibilities, then all of the boundary work will go toward the work output. I can realize all the boundary work as a work output. By the same token, if I have irreversibilities in a compression, then I will need more than the minimum work required for a reversible process, because I will have to overcome the friction between this piston and the walls of the cylinder. So I will have more work than the minimum, which is true for the reversible quasi-equilibrium processes of compression. Now, the energy balance for this process can be written as follows. You have reversible heat in differential amount minus a reversible work out. Let's talk about turbines, for example. You have turbines give you work out. So the difference between work and heat will be equal to, of course, internal energy plus boundary work, so differential amount of enthalpy, so dH, plus changes in kinetic and potential energies. But note the following. It's the definition of the entropy. So this reversible Qn is nothing but TdS. And TdS from the second TdS relation is equal to dH minus VdP. So if you combine these, you'll get that delta Q n is equal to dH minus VdP, just these two equations. And if you substitute this dH and this dQ into this equation, you'll get that minus W is equal to VdP plus these two. Okay, so if you integrate this equation, you'll have delta PE, delta KE, and minus the integral of VdP. Of course, minus. This is plus, becomes plus, and this is minus, this is minus, this is minus. So plus sign here and 3 minuses. What does this say? This equation tells me that the reversible work output, let's say for a turbine, is equal to the difference in boundary work minus difference in boundary work minus difference in kinetic energy minus difference in potential energy. So whatever potential energy this gas that expanded in a turbine lost, I gained as a work output. Whatever kinetic energy this gas that is expanded in a turbine lost, I gained as a reversible work output. Whatever boundary work it lost when it expanded, because it did the boundary work, it's a boundary work out. I gained as a work input. So let's say the boundary work in an expansion is 5 kilojoules. So this is 5 and a plus. This is minus because work out. So this is minus minus plus the kinetic energy. Actually minus the kinetic energy minus 2 or 3 minus 2. So all of these contribute to the work output. This equation gives us the reversible work output, okay, associated with an internally reversible process. I specified this is work reversible process in a steady flow device. It will give a negative result when the work is done on the system, like pumps and compressors. So work input, I'll change this to work input, and this will be minus the boundary work I put in. So this is plus, and this is plus, and this is plus. Kinetic energy, potential energy, and kinetic and boundary work. What this is saying is that the minimum work input is whatever I increase the potential energy and kinetic energy of the fluid that is being compressed, plus whatever boundary work I need to put into the fluid being compressed, and nothing else. I don't need an extra something for the irreversibilities, for example. No, because this is a reversible process. If this was an irreversible compression, then I would need more than these three terms. So suppose I want to increase the potential energy by 5, kinetic energy by 3, and I want to add 2 kilojoules of boundary work, then I will need 10. However, if this was an irreversible, you cannot have 10, you cannot have 2, 3, 5, because there are, again, 3 or 4 or whatever kilojoules that goes into the irreversibilities. So this will be like 13 or whatever. For an incompressible fluid, the specific volume remains constant during a process. So this integration is easy. And you can remove this outside the integral, and this will be just V delta P. Note that the larger specific volume, the larger the reversible work produced or consumed by the steady flow device. So if this was a pump, then it's to my advantage to decrease this V as much, to minimize this as much as possible. If this was a turbine, then I want to increase the specific volume. So recall that turbine process diagram. What does this mean? This V increase or decrease. If we were to compress the liquid exiting the turbine without losing its heat in the condenser, we would put in all the work we obtained in the turbine in the compressor and not gain any work output. So I want to maximize the area within between the compression and expansion, and this net area is the one that maximizes the work input for the cycle, as we saw in chapter 6. For the steady flow of a liquid through a device that involves no work interaction, so this term is nothing. I don't have any work like a nozzle or a pipe. The work term is 0, so these three things are 0. This is called the Bernoulli equation, and it's used heavily in fluid mechanics. Basically, it relates. It's a conservation of energy, basically. So you have like a velocity head and elevation head and a pressure head, and they all have to match. They have to be equal. So we might talk about this later. Okay, so this is about the reversible workflow we want to shoot for. Now, is reversible better? Is the work reversible work or the work for a reversible turbine better than or greater than the work produced by an irreversible or an actual turbine? The answer is yes. And the work required by a reversible compressor is less than the work required by an irreversible compressor. And this is why we say this. The steady flow devices deliver most and consume the least work if the process is reversible. There's a couple of pages, a couple of paragraphs in your book that discusses this. So please look at this at your convenience, and this will show you that this is true. Okay, if this is true, then it's to our advantage to minimize the compressor work. But how do we do it? Well, we have a hint. We want to minimize the compressor work because the less we take off the turbine work output in order to compress the thing in a compressor, the more net work out the cycle will deliver. So instead of the turbine delivering 100 megawatt and then the compressor shaving off 10 megawatt for the compression process, it's to our advantage to minimize the work required by the compressor so that it needs only, not 10, it needs only like 8. And this will increase the net work output of a cycle. So if you neglect the kinetic and potential energy changes, this work reversible reduces to the boundary work. So one way of minimizing the compressor work is to minimize the irreversibilities, of course. No friction, make it as smooth as possible, no turbulence, no non-quasi equilibrium processes. You minimize all of these. But this is not always very practical. I mean, there's a limit how smooth we can make the parts, or how slow we can make the flow, or how slow we can make the compression. So there is a limit to all of that. A second approach, and more practical, is to keep the specific volume of the gas being compressed as small as possible during the compression process. So keep this as small as possible, and this means temperature must be minimized as small as possible so that specific volume remains as small as possible. So this means I have to cool the gas as it is being compressed. We'll look at 3 kinds of processes. An isentropic process involves no cooling, just no irreversibilities, but no cooling. And a polytropic process that involves some cooling. Of course, there are some irreversibilities, I'm guessing the actual thing. And an isothermal process, well, it is the best. It involves the maximum cooling. So you compress it, and you notice the pressure has increased of this ideal gas, so you cool it, and you compress it, and then the temperature increase, and the V increases, specific volume increase, and you cool it again, and you keep doing this. So you keep this V as small as possible. Let's look at these. If I have, assuming all 3 processes are executed between the same pressure levels, P1 and P2, so this is the final pressure, and this is the initial pressure. I have my fluid here, and I want to compress it. If you do it isentropically, it will just go this way. If you do it polytropically, it's in between, and if you do it isothermally, this will be the least amount of work. Notice that the area, this VdP, it's not a PdV, it's the area to the left of the process. So this is for the isothermal, and this is for the polytropic, and this thing is for the isentropic. We've looked at these before. These are just the boundary work, the integration of the integration of the boundary work term, and you'll see that this is not possible. This isothermal process, while it is the best, it's not very practical. I cannot keep on cooling. I give it like 1 millijoule and I notice an expansion, an increase in V, and then I cool it. So I have, and then I compress it again, and I cool it, and I do this for 100 million times. I need 100 million stage for the compression. This is impractical. The way people do it is to use multi-stage compression, and they limit it to just 2 compressions. So I have compression, the high pressure compressor, and the low pressure compressor. They do it this way. This is T versus S. My best compression is the isothermal, so I'll keep doing this. So compress, cool, compress, cool, compress, cool, compress, cool, until you reach the final isobar. In reality, I cannot do this, so I'll do a polytropic process. So I'll compress it to an intermediate pressure, and then I'll cool it, and then I'll compress it again to my final pressure, because I need from P1 to P2. What this gives me in terms of the PV diagram is a process curve that looks like this. So a compression here, and then an intercooling, and then a compression here, and I reached my final pressure. So this area is the work saved. Instead of 9 kilowatt, I took 7.5 kilowatts or whatever. So what is this Px? How do I break them? How do I do stage 1? I compress it until what pressure, and start the second compression process. Well, the only variable, if I write the work for the compressor in for the whole process, the first stage and the second stage, these are all polytropic, so these are the same. This is equal to this. The only difference is that this is going from P1 to Px, and then this one Px to P2, excuse me. So this is the first step, and this is the second stage. Now, if the only variable in this equation is Px. The Px value that will minimize the total work, I want to minimize this. So I'll determine I want to minimize the work of the compressor by playing with this Px. I know my initial pressure, I know my final pressure, but I don't know the value of Px that minimizes this work input for the compression. So of the compressor, the compression process overall. So I'll differentiate this expression with respect to Px and set it equal to 0, and I'll get this. So, or I'll get Px over 1 is equal to P2 over x. So this tells me that the ratio of this compressor has to be the same as the ratio of this compressor. So if I'm compressing it from 1 kilopascal to 10 kilopascal, then I'll have to go, the first compressor will take it from 1 to 3.333, and then the second compressor will take it from 3.333 to 10. Or if I'm doing it from 10 to from 1 kilopascal to 100 kilopascal, this thing will be 10. So from 1 to 10, and then from 10 to 100, and so on. Irreversibilities, let's talk about something called isentropic efficiencies of steady flow devices. Irreversibilities inherently downgrade the performance of devices. So irreversibilities are bad. It is desirable to have a parameter that quantifies the degree of degradation due to irreversibilities. I know they degrade the performance, they worsen the performance of these devices, but I need a number, I need to quantify, I need to put a number. This degrades it by 50%, or this degrades it by 10%, I'll take the 10. This degrades it by 0%, so it's actually reversible. For cyclic devices that we studied in chapter 6, this was done by comparing the cycles with the irreversible processes such as the Carnot cycle. So I'll compare my actual heat engine to the Carnot heat engine, and I'll see, well, if the Carnot heat engine has an efficiency of 60 and my device has efficiency of 59, then I'll be happy. For steady flow devices, I don't have such a thing. This will be done for steady flow devices by comparing the devices that follow the ideal process. What is the ideal process? I have an actual turbine. I want to compare it with something with the best possible turbine. Well, this is the ideal turbine. The ideal turbine is one that involves no irreversibilities and no heat transfer. So it's a reversible and an adiabatic compression and an expansion in a turbine. In other words, it's the isentropic expansion, isentropic process. So if you want to compare your actual turbine to something, compare it to the isentropic turbine. The resulting parameter of this comparison between the actual and the isentropic is called the isentropic efficiency, which compares the performance of the device, whether it's work output, work input, increase in kinetic energy, whatever desired output of the device, to that of an isentropic device. I'll just compare it to the performance of the isentropic device. For example, the isentropic efficiencies, I'll study 3 or 4 of them. The first one is for a turbine. For a turbine, I'll call it eta sub t. So it's an efficiency. It's not a COP. It's actual efficiency. 100%, 2%, 5%, 0%, and the subscript T meaning it's a turbine. And this will be the actual work output for my actual. Sorry, this is hidden by the picture. This is the actual work output divided by the isentropic turbine work output. Of course, the isentropic turbine work output has no irreversibility, so this gives me the maximum. Meanwhile, the actual turbine work output is less than that. Well, the actual work output for a turbine is just difference in enthalpies, and the isentropic turbine work output is the difference in enthalpies of between the state 1, the inlet, and the isentropic state 2, which is not the actual state 2. So from pressure 1 to pressure 2, this is the expansion, the real thing. It increased in entropy. This is 2s, s2s. So the entropy of the second state, the isentropic. If it's the actual thing, sorry, A. This is A. If it's isentropic, then the entropy did not change from state 1 to state 2. So this thing was the same. Okay, and this guy is the isentropic drop in enthalpy, while this thing is the actual drop in enthalpy. Okay, of course, you see that this is smaller than this. Okay, why did this increase? Because some of this work input, some of this kinetic energy, some of this flow work of the actual turbine translated into, due to irreversibilities, to heat, friction, and an increase in temperature, and an increase in entropy. Okay, if it had no irreversibilities, no friction, nothing, then the temperature of the exit at the actual state would not be as high. It will be lower, and all of the work, all of the energy will be converted to useful work. However, the actual turbine will not do this. It will translate some of this kinetic and some of this enthalpy difference into work output, useful work output, and a small amount, I hope, into heat irreversibilities. Same story with the compressors and pumps. So the isentropic efficiency for a compressor, so eta sub c, is because it's a work output device. I expect the isentropic pump to or compressor to consume less work So this will be actually smaller than this. So the isentropic work input for a compressor is less than the actual work input for a compressor, because the actual compressor has lots of irreversibilities in it, friction and whatnot. So this is the opposite of the turbine. So this is the isentropic on top and the actual at the bottom. You see the HS diagram here, that from going from pressure 1 to pressure 2, from this isobar to this isobar, instead of the thing being isentropic, the entropy increases actually for the actual case, and the actual enthalpy, or basically the temperature of the fluid at the exit of an actual turbine is greater. Okay, and the work required is greater. By the same token, if I have a pump, then again the isentropic work is less than the actual work. But if I have a pump, then this isentropic work is just a difference in enthalpy. I'll just use V delta P because it's an incompressible substance. For compressible, so I'm comparing the actual performance of an actual compressor or an actual pump to the isentropic pump or compressor. However, if I have a compressor with multi-stage compression with intercooling, for example, then the ideal process is not the isentropic process, but it's a reversible isothermal process. So I'll get this somehow, some way, and compare it to the actual work to it. So it's not an isentropic process that is the ideal, but the isothermal process, which is ideal if I have multi-stage compression. Lastly, the nozzle. Well, the idea of the nozzle is to increase the kinetic energy of the fluid. So the actual kinetic energy will be less than at the nozzle exit will be less than the isentropic kinetic energy at the nozzle exit, because the actual kinetic energy, the energy that got in here, some of it went into kinetic energy and some of it went into heat. Whereas the isentropic nozzle did not have any heat transfer, no irreversibilities, and all of it showed up as an increase in kinetic energy. So actually this one is greater than this one. In terms of diagrams, which compares again this HS diagram, so this is the first law, this is the second law. You have actually the temperature of the actual exit state is higher than the isentropic state. So due to friction and irreversibilities, some of it was converted to heat. Now note that for an open system, we have this first law. Okay, so change in differential change in temperature, in energy. Sorry, no need for this. Sorry. This is heat, work, output, difference in enthalpy, and then difference in kinetic energy. Assuming adiabatic zero work, steady flow through the nozzle, so still talking about the nozzle, then this difference in enthalpy is the difference in kinetic energy. And this is a smaller number than this, and if you square them, this will be almost zero. So this guy will be just the difference in just the kinetic energy at the exit. So V2 squared over 2. Okay, this is for nozzles. Let's talk about entropy balance. The second law of thermodynamics, this is the final topic in this chapter, which is the most important topic. The second law of thermodynamics states that entropy can be created but cannot be destroyed. The usual balanced equation applied to entropy states that total entropy entering the system minus total entropy leaving the system plus the entropy being generated is equal to the net change in the total entropy of the system. So let's talk about these three contributions, 1, 2, 3, one by one. Let's first take the entropy change of a system. Entropy change of a system is S final minus S initial, S2 minus S1. If the properties of system are not uniform, then the energy of a system, the entropy, of a system can be determined by integration, just like we did for the energy and for the mass. So the entropy per unit mass, or you could integrate this over the whole volume. Now, if you want to compare this, the mass balance, energy balance, and entropy balance, this has an extra thing. Entropy can be generated. Okay, so that's the entropy change of a system. We'll look at it shortly again in detail. Let's talk about the next one, which is S2 Sn minus S out. So how entropy can get into or out of a system. Mechanisms for entropy transfer are two. Entropy can be transferred to or from a system by two mechanisms, heat and mass. By contrast, of course, energy can also be transferred in addition to these two. It can also be transferred by work. Heat transfer. A few pointers on heat transfer. Heat is a form of disorganized energy. Some of the wrongful interpretation of entropy is that entropy is the disorganization, which is not true. So if you believe in this, which is wrong, entropy will follow heat. Heat transfer to a system is an increase in entropy. Heat rejection is the only way the entropy of a fixed mass can be decreased. Entropy transfer by heat is just Q over T, if T is constant. The direction of entropy transfer is the same as the direction of heat transfer, since absolute temperature T is always positive. Okay, these are some pointers on heat entropy transfer by heat. If temperature is not constant, then the entropy transfer during a process can be determined by integration. I have to integrate this, and if I have to integrate, I have to have a functional relationship between T and Q. I have to know this as a function of the other. Or I could say this is the summation of the Q K over Tk, meaning I have part of the Q transferred over this temperature and this much Q being transferred over this temperature, and so on. I'll break them up by boundary location, where Qk is the heat transfer through boundary at temperature K at location K, temperature Tk at location K. When two systems are in contact, the entropy transfer from the warmer system is equal to the entropy transfer to the cooler system at the point of contact. This is only Sn minus S out as it pertains to heat transfer, not the total entropy balance. Okay. The second thing is the mass flow. Let's first talk about work. We'll say that work is entropy free, so there is no entropy transfer with work. Work is clean energy, it's organized energy. We like work. An energy interaction that is accompanied by entropy transfer is heat transfer. By entropy transfer is heat transfer. This is another way to define energy, or to define heat or work. You know, here heat is entropy. Heat is energy transferred due to a temperature difference. Well, heat is energy transfer that is accompanied by entropy transfer. Is another way to define it. And an energy interaction that is not accompanied by entropy transfer is work. So you have two definitions of heat. Okay, let's talk about the second way entropy can be transferred to a system, which is mass flow rate. Mass flow in or out. Mass contains the entropy. Mass contains entropy as well as energy, as well as many other things. So when the mass of a system is doubled, so are the entropy and the energy content of the system. A closed system do not involve any mass transfer, and thus any entropy transfer by mass is not there for closed system. Entropy transfer by mass is just m times s. Okay, this is per unit mass. This is the actual thing. The entropy of a system increases by ms when the mass in the amount of m enters and decreases by the same amount when the same amount of mass at the same state leaves the system. This is the same old problem. We need to see, or we need to determine the property S of the mass coming in and out. Remember, during unsteady processes, we were faced with problems, and we reduced them to 3 special cases I talked about in class. If the properties of the mass change during the process, the entropy transfer by mass flow can be determined by such equation. So S dot mass is equal to this S rho times velocity, local velocity, normal to this, and the entropy transfer by mass is integral across the whole cross-sectional area, which is given by the normal velocity, as well as you can integrate this with respect to time, and it'll give you the mass transfer contribution, the entropy transfer by mass contribution. Last part of this entropy balance is the entropy generation. This entropy generation term, we can make the following comments. Irreversibilities always cause the entropy of a system to increase, so this will always be positive. Examples of irreversibilities are friction, mixing of two things, chemical reaction, heat transfer across finite temperature differences, unrestrained expansions of gases, non-quasi-equilibrium expansions or compression in general, and so on. You can add plastic deformation. You could add many other things. For a reversible process, no entropy generation takes place. So you can define a reversible process in such a way that takes into account this entropy generation. No entropy generation means reversible process. So entropy balance for in the reversible case becomes analogous to the energy balance relation. So if you can eliminate this, then this one, energy in minus energy out, equals delta energy for the system for a reversible process. However, the energy change of a system equals the energy transfer for any process, but the entropy change for a system equals the entropy transfer only for reversible process, like we said a moment ago. Okay, these are the forms, the general form for the entropy balance. We're going to use it extensively. Entropy balance can be written for any type of system as follows: net entropy transfer by heat and mass plus the entropy generation is equals to the change in entropy of a system. In the rate form, this is kilowatt per Kelvin instead of kilojoule per Kelvin. This looks like this, and on a unit mass basis, if you divide by the mass, this will look like this, so kilojoule per kilogram Kelvin. And a process for which S gen is equal to 0, which is internally reversible, but not necessarily totally reversible, because the generation could happen outside the system. So we'll talk about internally reversible processes. So special cases, closed systems. A closed system involves no mass flow across its boundaries. So a big part of the entropy balance went away. Its entropy change is the difference between its initial and final entropies, and entropy change of a closed system is due to entropy transfer accompanied by heat transfer and entropy generation. These are the only ways you can affect an entropy change of a closed system. The general form for the entropy balance of a closed system is as follows. So no irreversibilities, I mean no mass inlet. So this guy will equal to the change in entropy, and this is just due to heat transfer, no mass transfer, plus the entropy generation. If I have an adiabatic process, then this goes away, and I'll have the change in the entropy of a system is equal to the entropy generation. And a closed system and its surrounding, I can always take them together to be as an adiabatic system, because there is no heat transfer between the system and the surrounding if I take them all the system. So like an isolated system, if you remember them. So Sgen is equal to the summation of the entropy changes for the system and the surrounding. For the system, I can get using tables or whatever means I can. For the surrounding, I have no properties for the surrounding, but I know that this is just Q divided by T for the surrounding, if this is constant, or else I'll have to complicate things and do some integration. Okay, so this Sgen is equal to delta S for the system plus delta S for the surrounding. Okay, and these are the following. Formulas. So I'll need this in many situations. Finally, I'll say that the entropy balance for a control volume, the entropy balance relation for a control volume, the open system, differs from those for a closed system in that they involve one or more mechanism of entropy exchange, mass flow as well as heat flow. So mass flow across the boundary are present here. The general form is as follows. You have entropy transfer by heat. Of course, this is in or out, depending on the value of Q. I don't have to say Q in minus Q out. I just put it as a number, and it's a directional quantity, so it takes care of itself. Plus the mass in, the entropy with the mass in, and the entropy going out, and plus the entropy generation is equal to the change in entropy of the system. In a rate form, I'll dot these things, and in the steady flow processes, this will go away. So Sgen will be equal to Se minus Si minus Q. Okay, and this is very important. Source of confusion. This is minus, and this guy is in relation to the system. So in is in positive, and out is out positive E. So don't change the sign of this heat transfer just because there is a minus sign here. We'll see an example on that. For a single stream, I don't need these summation signs. So this will be just m dot Se minus Si plus or minus summation of the locations of heat transfer. If I have this system and there's heat transfer across this boundary, heat transfer across this boundary, T1, T2, T3, I'll sum of them. This is Q1, Q2, Q3. I'll sum all of these. Adiabatic, so no heat transfer. This will be just single stream, steady flow. This will be the case. Okay, and this gives me the general case. I think it's a picture out of your book. Last thing I want to talk about is the entropy generation associated with heat transfer. You remember we said this, that if the system boundary are here and the actual temperature drop or the heat transfer happens outside the boundary, then the entropy generation happens outside the boundary. This is internally reversible. So the wall is ignored. When the wall is considered, then in actuality, this entropy generation happens within the wall, because this is where the non-isothermal heat transfer happens. And if I include this within the system, then this irreversibilities happen within the system. Lastly, if you have an actual case where the temperature stays at high temperature and then drops near the wall before it reaches the boundary, and then keeps dropping throughout the wall, and then drops slightly before it stabilizes outside, then there is an entropy generation inside the system and outside the system in the boundary.